So hello to everyone joining us today. My name is Halleluya-Ekandjo, and I'm the Vice President for the National University of Ireland SEG Student Chapter, and also part of the Symposium Organizing Committee. On behalf of the NUI SEG Student Chapter, I'd like to welcome you all to the SEG Student Chapters Earth Day Symposium, a forum to reflect on the challenges, the aspirations, and the role of the students and early career economic geologists in the world experiencing rapid climate change and other ecological and societal changes. Today, we celebrate and honor Earth Day, an international event which is celebrated around the world to pledge support for environmental protection. The year 2021 marks the 51st anniversary of the annual celebrations, and the theme for Earth Day is Restore Our Earth. We geologists have a role to play in restoring Earth, and I encourage everyone to make the right choices for a greener and healthier planet. Just a bit of housekeeping before we get to the business of the day. We have a code of conduct for this event, and it will be posted in the chat. Please read it through, but overall, let's just be respectful to one another. Submit questions for the student speakers or panelists into the chat box. If these are directed towards a particular speaker, please start a message with your name. The chat box will be monitored by us, the NUI student members, and the questions will be directed to the relevant person. This will be answered during the question and answer session, time permitting. We also like to ask you please to keep your mics on mute at all times. And lastly, this is a learning event for all of us, so please feel free to ask questions via the chat. Let's listen, let us learn, and let us engage. Now into the business of the day. We have received a wealth of amazing contributions from the SEG student members and from professional geologists. And while we won't be able to broadcast every contribution in the full during this live session, they are available on our YouTube channel, and we encourage you to watch them in your own time. The YouTube channel link will be posted in the chat as well. This live session consists of student research presentations and Q&A, followed by a panel discussion, all accompanied by short videos showcasing the perspectives, motivations, and thoughts of students and economic geologists from all around the world. Besides showcasing research from the SEG students and discussing challenges and opportunities for economic geologists and as a discipline as a whole, in a changing world, a key goal of this event is to network and to create spaces for future collaboration. This event is meant for us to listen, to learn, engage, and hopefully get inspired by different generations of economic geologists. So please feel free to ask questions at any time by placing them in the chat box. A big thank you to everyone, especially those who directly contributed and helped in other ways. Now we are going to listen to the message from the SEG President Moira Smith and Chico de Avenzo, the President-elect. Enjoy.
Hello, everyone. My name is Moira Smith, and as you may know, I'm your SEG President for 2021. I'm honored to represent the most prestigious economic geology organization in the world. This last year has been a challenge, and I regret that I probably will not be able to meet a lot of people in person this year due to COVID constraints on travel and gathering and whatnot. But as I like to say, the silver lining is that SEG has really upped its game in terms of online offerings, including webinars, meetings, collaborations with groups like Ore Deposits Hub, and that provides a greater reach and opportunity for people who ordinarily would not be able to attend a meeting or other offering in person. And perhaps, given that you were raised in the digital age, the students and early career professionals are really leading the way in this regard. So kudos to you. David asked me to tell you a little about myself in honor of the SEG Student Chapters Earth Day Symposium. So here goes. I was very fortunate to grow up on the west coast of the US with big volcanoes always on the horizon. I started climbing, skiing, and mountaineering at an early age, and that's what motivated me to learn more about what I was walking over and looking at. Well, 3 degrees later, and after learning a lot about structural geology and tectonics, I still hadn't clued into economic geology as a career path. I joined the British Columbia Geological Survey, and I worked alongside ore deposits and economic geologists for 4 years, so kind of easing into it. One of the most memorable moments was when I first started with the BCGS. It would have been about 1991, I think. I had a freshly minted PhD and I was in a remote field camp, and I was eager to meet one of the legends of economic geology who discovered a very large copper deposit that we were mapping around. So after I explained what we'd mapped and learned over the last several weeks, he turned to me and declared that in the morning, he wanted his eggs cooked over easy with brown toast, buttered on one side only, thank you. I was devastated, but I didn't let that slow me down, and you shouldn't let momentary setbacks slow you down either. We've come a long way since then, and SEG in particular is making great strides in making sure that everyone feels included despite a relatively restricted past. Anyway, I made the jump to industry in 1996, better late than never, and I've never looked back. If I have any advice for people thinking about a career in economic geology, that is to just go for it. You've got the whole world and a huge number of deposit types to choose from. So right now, you don't necessarily need to specialize in economic geology unless you want to, of course, especially at the exclusion of other geological disciplines, because a basic grounding in a wide range of subjects will get you a long way, and you can learn the rest on the job. I've worked all over the world, but here in the Great Basin, for example, I've had to put to use such diverse subjects as stratigraphy, tectonics, structure, geochemistry, even paleontology. That being said, one thing that is essential these days and in high demand is at least a working knowledge of GIS and 3D modeling software. So if there's any opportunity for this at all, don't leave school without it. Another message, given the theme of the symposium, is that economic geology is more relevant now than ever. We've all heard the old trope that if it can't be grown, it's got to be mined. But let's think about that for a minute. The world is moving at an accelerating pace toward demanding reduced greenhouse gas emissions and clean energy solutions. These things are very metals intensive, and the World Bank recently published a report suggesting that the consumption of metals like lithium, cobalt, rare earths, nickel, and a whole host of other metals will skyrocket over the next several decades. And many of these are produced in a very few countries with rather checkered human rights and environmental records. So that's where SEG can play a role in raising awareness and helping to give us the tools we need to find more deposits and support the clean green economy. On that note, I'd like to invite you to the SEG Denver 2022 conference, which will have an emphasis on clean energy metals. And if you'd like to help out in planning it, we would certainly welcome you. In the meantime, I hope you have a great symposium.
Hello everyone, my name is Chico Azevedo. It's an honor to join you in this Earth Day Symposium. I am a geologist by training and dedicated my career to mineral exploration. I got my geology degree from University of Brasília in Brazil in 1983. I decided to study geology because I had a curiosity in natural sciences, but I have to confess that it was not until the second or third year uh, until I could realize that geology had been the right choice to me. The step towards economic geology was taken still during my times in university, when my country started an interesting debate on the development of the huge iron ore resource discovered in the Carajás province in the Amazon region. This debate proved to me that major mineral provinces and the mine industry can be very important for developing countries like Brazil. Immediately after leaving university, I was offered a job in a gold mine in Minas Gerais state, Brazil, not far from where I'm talking to you now. The mine was owned by a South African company, Gencor, where I worked for 14 years, with great opportunities in training, traveling, and also good mentoring. In my last 2 years with Gencor, I was transferred to Argentina and developed a research project to evaluate gold potential in rocks of Paleozoic age in the Andean region. My next job was with IM Gold Corporation, still based in Argentina, where I explored for gold in Argentina and neighboring countries. In 2006, I joined Goldfields as exploration manager for South America and concentrated efforts in Chile and Peru mainly. About 4 years ago, some colleagues and I started an exploration company, Turmalina Metals, where I am an executive director. On the day we get together, at least virtually, to celebrate Earth Day, I'd like to share with you some thoughts that I consider relevant to this venue. I think we, economic geologists, have made a significant contribution to the construction of this modern world, not only with the discovery of the mineral deposits to replace the resource and reserves mined every year, but also with the discovery of the new materials necessary for this industrialization process. However, when we look forward and consider the estimated demand for metals and minerals to continue this process of modernization, it becomes evident that we have important challenges ahead. To address this challenge, I think we need to look our recent past before we look forward. In these times of increasing environmental awareness, the level of negative perception of the mining industry is high and increasing. This perception is caused by several factors, including the many occasions where the mining industry has performed poorly. And this is one of the tasks we have as economic geologists, in my opinion. Make sure we continue to modernize our industry, and more importantly, we operate responsibly, starting with the exploration program, passing through the mining operation phase, and eventually the closure, mitigation, and post-closure monitoring processes. I would like to add another challenge, also based in past experience, the difficulty that we have to communicate and interact with other sectors of the general society. Several factors contributed to this, including the lack of understanding by this general society of the importance of metals and minerals to their quality of life. But this should not prevent us from finding a way to break this wall and start discussing more broadly with other sectors the solutions for the challenge we face. Big challenge, no doubt, but I believe we have a chance to succeed for some reasons. And one important one is the fact that 20 years ago, the Society of Economic Geologists intensified efforts to attract young talents to the study of economic geology by funding research grants, fellowships, field trips, courses. And we were successful. Today, we have 109 active student chapters in 31 different countries. The simple fact that we are participating on this symposium shows that this body of students and early career professionals are taking actions to start debating the challenges presented and find the solutions that our planet and our society demands. So, to finalize, I would like to pay my compliments to the student chapter of the National University of Ireland for the initiative of this symposium, and also to say thanks for the kind invitation for me to participate. Thank you for your attention.
Thank you, Mara, for the amazing keynote words and for sharing your stories and also for the advices that you have given to us, early career and the future generation. I've learned so much, and I'm hoping that everyone listening has taken a word or two from what you have just shared. So we're going to move on to the technical part one, where we're going to listen to 3 talks from students from all over the world. And then after the 3 talks, we're going to have a Q&A session, and then we'll move on to the next 3 talks and then another Q&A session. So over to the technical talks.
Hello everyone, my name is David Kaeter and I just completed my PhD at University College Dublin and ICRAC, where I studied lithium pegmatites in southeast Ireland. Currently there are two principal sources for lithium. One of them are subsurface brines below South American salt lakes and the other one are hard rock deposits in the form of lithium pegmatite. And have typically much higher ore grades, up to 1.58% of lithium per kilogram of rock, but they are typically rather small and only very exceptional pegmatite deposits reach more than 2 million tons of total lithium. Taking a look at a brine operation in the Salar de Atacama in Chile, we see that these operations have a huge spatial footprint. The scale by here is 6 kilometers, and the whole operation is not only these brine pools you can see here, but also between the brine pools we have a grid of boreholes which extend beyond the image. The Salar de Atacama alone provided 22% of the world's lithium in 2020, and another 20% or so comes from other brine operations, mostly in South America. When we take a closer look at these brine pools, the scale by here is 600 meters, and the brine is pumped from below the salt flat into these pools to evaporate to reach the desired lithium concentrations. And this is a rather slow process. It takes about 1.5 up to 2 years until the brine reaches the desired concentrations. So production can only be ramped up very slowly. In addition to that, this is a very freshwater intensive process, and these deposits form in the driest places on Earth, which potentially causes problem to the local communities and environment. When we take a look at an example pegmatite mining operation, this is Greenbushes in Western Australia. We see that these have a much smaller spatial footprint. The larger pit here has maybe a diameter of 800 meters. The scale by here is 1 kilometer. And currently mining actually happens underground in this site. Most of the hard rock lithium currently is mined in Australia, and Australia almost provided 50% of the world's lithium in 2020. But they didn't produce the lithium. What's happening is that the spodumene ore concentrate, which contains only a few weight percent lithium, is shipped all the way to China, where it's processed into lithium carbonate and other lithium chemicals, which can be used for further production. When we take a closer look at this pit here, it's called the Cornwall pit. We see the pegmatite body, which is being mined here in white. Greenbushes is mined for lithium, but important byproducts are tin and tantalum, which are often regarded as critical elements as well. And Greenbushes actually started as a tin mine, which is reflected in this name, Cornwall pit. Besides uses in lightweight aluminum alloys, ceramics, glassmaking, and pharmaceuticals, the most important use of lithium is in rechargeable high-energy density batteries. And in recent years, there was a first boom in lithium demand driven mostly by consumer electronics, but now, and especially in the foreseeable future, the main driver of lithium demand will be electronic vehicles and renewable energy storage systems. The most important use of tin is in electric solder. In 2019, nearly 50% of the world's tin production was used for solder, and even though electronics are increasingly miniaturized, the absolute demand for tin solder is assumed to rise. And another 7% or so are used in lead-acid batteries, and a large share of that is used for electric bicycles in China. Tantalum is another element important for modern electronics and is used for capacitors. Tantalum capacitors were crucial for the size reduction of mobile phones in the 90s, and it's one of those elements that is responsible for the fact that we are able to carry powerful computers in our pockets. So because of its use in batteries and for electric vehicles and renewable energy storage, lithium is one of the key elements for decarbonization, which makes it important for sustainable cities because these can only be sustainable with strongly reduced carbon footprints. Building of infrastructure for renewable energy and electromobility will not only require lithium, but also a range of other metals, including tin and tantalum. Apart from that, the current lithium production is neither green nor sustainable because of the problems I mentioned earlier involved with brine production and the long marine transport routes involved with production from Australian spodumene in China. So if we would have more domestic supply chains, more responsible production and consumption would be possible. So proper sustainable development would mean that we have exploration and eventual production, for example, locally in Europe or other jurisdictions. So how does geological research fit into this? Here we see the cycle of any mined material. The first 4 steps are exploration, mining, processing, and the raw material. All geology, mineralogy, and geochemistry research comes even before that, and especially feeds into all of these first steps. Ideally, we would like to reach a circular economy, but for the foreseeable future, recycling can only supplement the growing demand. So what does this mean for research on lithium pegmatites? First of all, deposit models for lithium are not nearly as advanced as for high demand metals such as copper. Exploration models for lithium pegmatites are limited and not widely applicable. Vegetated and glaciated terrain, as typical for Central and Northern Europe, for example, poses additional challenges to exploration, and the poorly understood but complex internal structure of lithium pegmatite deposits has direct implications for mining and processing. So let's have a look at the lithium pegmatites in Ireland. Here we see a geological map of the southeastern Ireland, and in red we have the late Devonian, late Caledonian Leinster batholiths, and on the eastern flank we have a major regional shear zone, the East Calder Deformation Zone, and within this shear zone we have the Leinster lithium pegmatites. Taking a bit of a closer look, we see that the pegmatites entreat both granites of the Leinster batholith, but also Ordovician metasediments and metavolcanic rocks, and these pegmatites coincide with the Kilkerry member, which are andesitic amphibolites, as well as the Monorco member, which contains tourmalinites and corticules. And when we follow this trend further to the northeast, we encounter tin tungsten vein deposits, and further northeast we actually have also some subeconomic gold quartz veins. So let's have a look how this might look in an idealized cross-section. We have the Leinster batholiths here, and we think that the lithium pegmatites formed from small batches of anatectic melt that formed in the East Calder Deformation Zone. These melts were trapped and formed small igneous bodies. And what I'm going to do next is walk you through a model for the internal evolution of these pegmatite dikes, followed by some evidence for this model. After emplacement, we start with magmatic crystallization of K-feldspar, quartz, muscovite, plagioclase, and we also see early spodumene, which is the main lithium mineral. We also see some early columbite, which is low in tantalum. As this pegmatite crystallizes, the residual melt you see here in between becomes enriched in rare metals, including tin and tantalum, but also alkalite metals like rubidium and cesium, as well as volatile like H2O and sulfur, as well as other fluxing elements like fluorine. And all of these elements affect the structure and the physical and chemical properties of the melt, which eventually leads to unmixing of a fluid or of a second melt, which causes in situ metasomatic alteration during crystallization of this pegmatite. This is shown in this image. We have still magmatic crystallization, but we also get formation of these quartz mica grisons. And this is the stage where we start to see cassiterite mineralization and, as I said, this in situ grisonization. As volatiles more and more become enriched in the residual fluids, we start to get into a third stage, which is characterized by hydrothermal processes. Here we see hydrothermal tin and tantalum minerals, which are hosted by pervasive albitites, and we also see evidence for interaction with the host rock and the formation of geochemical halos around the pegmatites. So let's take a look at some of the rocks. The early magmatic lithologies are characterized by very coarse-grained material. Here we have barren pegmatite, which only contains K-feldspar quartz, minor plagioclase, and muscovite. On the upper right, we see medium-grained spodumene pegmatite. Here we see coarser-grained spodumene pegmatite. And as crystallization goes on, we come into this, what we call the magmatic hydrothermal transition, where the late-stage fluids start to alter what is crystallized earlier. We see some examples here. We have some parts which show nice large crystals of the early magmatic lithologies. In stage 2, we got formation of these quartz muscovite grisons. And then in stage 3, we got formation of these pervasive albitites. Here, the main lithium is hosted in the early magmatic units, while tin and tantalum are enriched in the late metasomatic and hydrothermal units. We not only see evidence for this magmatic hydrothermal transition in the rocks themselves, we also see it on the scale of individual minerals. And here we see a backscattered electron image of a columbite grain. It's strongly zoned, which is mainly zoning in niobium and tantalum concentrations. And what this grain records is essentially the 3 stages I just talked about. We have got an early core here, which was partially resolved and then overgrown by this mantle, which shows itself oscillatory zoning. And then we got another paragenetic gap here and partial resorption of the grain and crystallization of this very tantalum-rich rim. We also see this for trace elements. And we also see this not only in columbite, similar patterns and systematics are also observed and studied in white mica and cassiterite. And when you're interested in more examples and more details about this model, I would like to invite you to check out these publications. This mineral chemistry is not only useful to reconstruct internal evolution of LCT pegmatites, but it can also aid mineral exploration. When we look at regional stream sediment samples from the area, we see that catchments that contain these pegmatites show anomalous concentrations of tin and tantalum. And when we look at the mineralogy of these sediments, we find, for example, columbite, which shows very similar BSE textures, again indicating a multi-stage evolution. And we again not only see this in the major elements, but trace element patterns resemble what we observe in the pegmatites. And we see this for columbite, we also see this for cassiterite in the stream sediments. So anomalous tin and tantalum stream sediments is caused by cassiterite and columbite directly sourced from the pegmatites, and the textures and chemistries of these minerals are indicators of their source. To summarize, magmatic crystallization in LCT pegmatites is followed by metasomatic and hydrothermal processes which remobilize and redeposit critical elements. Lithium was deposited in early magmatic units, and tin and tantalum are enriched in late subsolidus units. The geochemical halos that form towards the end of the pegmatite evolution during the hydrothermal stage can point towards the LCT deposits, which is quite useful in exploration. And as we have seen with the stream sediments, the geochemical and mineralogical signatures that form during the magmatic hydrothermal transition transform into stream sediments, which allows us to use columbite and cassiterite as indicator minerals for these pegmatites. Thank you very much for your attention.
Good morning, good day, and good evening to all listeners. My name is Geboni Masilela, and I'm currently an MSc candidate from the University of the Witwatersrand in South Africa. Today, I will be presenting to you my master's project under the topic, The Black Reef, the Witwatersrand type deposit. The Black Reef is located in close vicinity to the enigmatic Auriferous and Uraniferous Witwatersrand supergroup. So why bother study the WITS, since most of the existing WITS gold mines will be closed by the year 2040, and gold production in South Africa has decreased over the past 3 decades because of energy and labor costs required to reach distal deposits, insufficient room for mechanized mining at kilometer depths, and unsafe working environments for employees at these depths. So the main question under this theme is, how does the Black Reef Formation contribute to sustainable development? Well, it has similarities to WITS type gold in terms of the style of mineralization, such as having Okean granite greenstone terrains in the hinterland, abundant iron-bearing phases in the form of pyrite, and abundant carbonaceous material. Therefore, the exploration and exploitation of the Black Reef Formation would provide an alternative to gold production and further sustain South African development for the future. Taking a deep dive into the area, the Kaapveld Craton hosts various Archean granite greenstone rocks, and these greenstone belts are overlain by the Dominion Group, Witwatersrand, Ventersdorp, and Transvaal supergroups. Later, emplacement of the Bushveld igneous complex took place, and the Vredefort meteorite impact occurred. The Neo-Archean Black Reef Formation, in blue here, is a thin and naturally extensive sequence of fluvial siliciclastic rocks at the base of the Transvaal supergroup. The Black Reef itself is a small to medium-grain quartz pebble conglomerate with deeply scoured channels which eroded into the footwall. The most prominent feature of the Black Reef is its abundant carbonaceous material in the form of pyrobitumen. It has significant concentrations of gold, uranium, and less PGEs. The most accepted source of gold is from reworked conglomeratic rocks of the upper Witwatersrand reefs and the Ventersdorp contact reefs. In the study area is in the Carltonville Goldfield, where the Carbon Leader Reef, the Middle Flay Reef, the Livingstone Reef, and the Fencerstop Contact Reef sub-outcrop against the Black Reef. In the East Rand, only the Kimberley Reef sub-outcrops against the Black Reef. The incised Black Reef channels intersect high-grade Witwatersrand Reef, which raises the potential for high-grade reef horizons through reworked channels. The Black Reef was also subjected to metamorphism, where low-grade sub-greenschiest metamorphic ashes have been recorded. In addition to that, loading of the thick transvaal sequence, emplacement of the Bushveld igneous complex, and the geological catastrophe of the Feuderford meteorite impact all caused post-depositional metamorphism of the Black Reef. In this study, 4 drill holes were used to undergo detailed core logging to record characteristics of the mineralized reefs and the overlying and underlying lithology. The simplified lithological logs show that the stratigraphy of the Black Reef begins with a medium to coarse-grained quartz ironite in the hanging wall, which has gold grades that are less than 2 grams per ton and associated with pyrite grains. The quartz ironite gradually changes to having scattered, sub-rounded quartz pebbles defined as a pebbly quartz ironite, which are characterized by gold concentrations of about 2 to 5 grams per ton and have pyrite grains which are hosted in a carbonaceous matrix. They are integrated with well-packed, matrix-supported conglomerate units. The gold concentration in these units ranges from 5 to 30 grams per ton in some instances, and the quartz pebbles are often embedded in a black carbonaceous matrix with abundant pyrite bitumen, which frequently occurs at the bottom contacts. These conglomerate units eventually find down to a carbonaceous shell with rounded pyrite nodules and pyrite orientated as stringers. In places, the carbonaceous shell is intercalated with gold-rich conglomerates, and these carbonaceous shells contain graphite in the matrix. Petrographic analysis was made in these units, and the quartz ironite samples show annealing and compacted quartz grains, and often the pyrite grains are orientated along bedding and cross-bed facets, and this is indicative of sedimentary formation. The carbonaceous shells usually have very fine-grained quartz. Specifically in the sample, there is grain size variation and fracture-filling carbonaceous material. The cubic pyrite grains are also observed, which is indicative of a hydrothermal fluid formation. The conglomerate rocks have fractured quartz pebbles that often contain carbon nodules and fracture-filling carbonaceous material. Areas where there is quartz straining have tiny gold specks within these extensional fractures. The petrography of the ore minerals show that there's various types of pyrite grains which have been classified by formation, such as massive detrital pyrite, random inclusion bearing detrital pyrite, concentrically laminated detrital pyrite, the euhedral orthogenic pyrite, and orthogenic pyrite overgrowth. The concentrically laminated detrital pyrites are the most important to distinguish because they consist of concentric sets of laminae, often with inclusions of gold in the interstices. Another important feature is that they are fractured, and this shows that they did not form in the Black Reef, but were rather transported from a sedimentary precursor with their preserved internal structure indicating a short travel distance from their source while carrying trace elements and gold between their laminae. The carbonaceous material also occur in 4 main subtypes based on morphology, such as fracture filling, mostly in shales, globular, which often contain the most irregular shaped and micron-sized gold and uranium minerals, nodular, which are relatively smaller and rounded, and irregular shaped, which occur mostly within the boundaries of pyrite. And lastly, the gold, where gold occurs as native gold along quartz microfractures and at pyrite pyrite grain boundaries. Fluid inclusion microthermometry in this analysis revealed that there are 4 main types of fluid inclusions at room temperature. That is two-phase fluid inclusions where the liquid is dominant, two-phase inclusions where the vapor is dominant, monophase inclusions with only a liquid phase, and three-phase liquid vapor inclusions where carbon dioxide is dominant. The average homogenization temperature or trapping temperature is 172 degrees Celsius, and the average freezing point temperature is -5 degrees Celsius. The salinity was calculated to be 7.04% sodium chloride equivalent, and the density was estimated to 0.948 grams per cubic centimeters. Raman spectroscopy also was used to define the concentration of the fluid inclusions, and the concentrations that were observed were H2O carbon dioxide, H2O carbon dioxide methane, H2O hydrogen sulfide, and methane inclusions, and these are very important in the later sections. Geochemistry reveals that the Black Reef sediments are related to their protosource. So that means that Archean felsic rocks of the Kapval Craton in the hinterland are the protosource rocks of the quaternite and conglomerate sediments of the Black Reef based on their correlation with zirconium, whereas the Archean mafic rocks of the Kapval Craton in the hinterland are the protosource rocks for shale sediments of the Black Reef based on elevated nickel and chromium content and the high magnesium number. The mean whole rock delta 34 alpha values of the study coincide with values obtained in the VCR and the Carltonville, Valcombe, and Klerksdorp goldfields from studies by Hoffman et al. 2009 and Guy et al. 2014. Therefore, the source of pyrite is the underlying strata of the Black Reef, and by inference, this provides evidence that the gold and the sediments in the Black Reef are mechanically sourced from the VCR and the Wits reefs. So how does all this data tie in together to form a metallogenic model for gold mineralization in the Black Reef? Well, the sediments of the Black Reef are derived from a protosource such as the Archean granite greenstone belt in the hinterland, and the sediments were deposited into the Wits and the Ventersdorp subgroups, where they were subsequently reworked and recycled into the Transvaal Basin. So due to mass balance calculations that were outlined by Fremel et al. 2005 and 2015, they show that the greenstone hosted orogenic gold sources in the hinterland could not produce all the gold content that is found in the Witwatersrand reefs for a purely sedimentary genetic model. So a more likely source is the entire Meso-Archean land surface of the whole Kapval Craton envisaged by Nwala et al. 2020. This land surface contained background concentration of gold. So in an anoxic environment with CO2 degassing from high volcanic activity, acid rain formed and caused chemical weathering, which leached out gold from its precursor host and transported gold to dissolved species in meteoric water. The gold was precipitated out of solution by oxidation when the fluids were in contact with photosynthetic cyanobacteria, seen as the microbial mats. This is the reason why the Carbon Leader Reef has the highest gold content in the Carltonville goldfield, gold that is associated with carbon seams. Further physical reworking of these delicate microbial mats formed fine-grained gold that was redeposited as paleoplaces in the Wits reefs and later into the Ventersdorp contact reef. It is therefore critical to emphasize that the primary mechanical processes followed by hydrothermal activity led to gold mineralization in the Black Reef. The mineralizing fluids are derived from devolatilization and dehydration reactions during diagenesis and emplacement of the Bushveld igneous complex, and therefore the fluids are sourced from a metamorphic and meteoric water mixing. The carbonaceous material in the Black Reef Formation is described as residues of migrating hydrocarbons generated by thermal maturation of organic matter through the oil window, which are temperatures reached through the fluid inclusion analyses of 172 degrees Celsius. The source of the carbon could thus be the shell units in the Volkberg group or the shallow marine carbonates in the Tunispoort group of the Transvaal Basin. And therefore, these are internally derived hydrocarbon fluids. Gold was transported as a bisulfide complex once it was dissolved. The presence of H2S in the fluid inclusions is known to assist in dissolving gold, while this carbon dioxide in the fluid inclusion is said to assist to keep the gold in solution. The geological catastrophe of the Vredefort meteorite impact caused secondary permeability and reactivation of pre-existing structures, which allowed hydrocarbon migration and remobilization of fluids, which have been circulating in the basement due to the Bushveld igneous complex, and this carried gold and other ore constituents. The erosional and angular unconformities also play a major role in directing the flow of fluids, which accounts for elevated gold concentrations at areas where the Black Reef is in contact with the Wits and the VCR. So based on Le Chatelier's principle, the precipitation of gold in this equation will be caused by the decrease in hydrogen sulfide species and the decrease in oxygen capacity or an increase in pH. The reaction of gold-bearing fluids with iron-bearing minerals depleted the sulfide in solution by forming pyrite or pyrrhotite and decreased the gold solubility. The interaction of fluids with carbonaceous metasediments also lowers the oxygen fugacity. This accounts for all the native gold found in close proximity to pyrite and irregular shaped carbon nodules. This shows that the main precipitation mechanism in the Black Reef is precipitation by reduction, and another gold trap in the Black Reef is the quartz microfractures, indicating that there was free gold. Thank you for your attention.
Hello everyone, I'm Hao Chengyu from China University of Geosciences Beijing, SEG Student Chapter. Thanks for Halleluya's invitation. It's a great honor to attend this Earth Day Symposium. The subject of my presentation is Peptide, a Kaeter mineral for mineral exploration. My presentation is in 3 parts. Firstly, protection and mineral exploration. The Earth is our home. The environment is closely related to our life. However, humans consume enormous amounts of resources, and environmental pollution have a beautiful Earth destroyed, not descent. But we need resources. We need gold as currency. We need all kinds of resources to make all kinds of equipment to promote social development. What should we do to maintain the balance? We could develop green energy, improve utilization, recovery, and methods of low-cost, low-polluted exploration. Second part, appetite for regional mineral exploration. Peptide is a widespread accessory phosphate mineral that occurs in many rocks and is relatively resistant to weathering. Peptide is useful in geochemistry or thermochemistry and therefore can establish the time, temperature histories of rocks. In addition, the crystal structure and chemistry of peptide results in accommodating high concentrations of many trace elements. Different rocks have different trace element information. Previous works therefore demonstrated that Peptide is effective in identifying types of rocks and regional mineral exploration. So we tried to apply peptide to mineral exploration at depth. The giant Mesozoic Jiaodong gold province has been estimated to contain up to 5,000 tons gold. More than 95% of the gold resource is hosted by Mesozoic granitoids and is controlled by northeast to north-northeast trending faults. The ores are mainly divided into disseminated stockwork type and coarse-vein type. Much of the gold mineralization events occurred at about 120 million years. In recent years, mineral exploration has focused on progressively deeper targets as the new surface explorers and shallow deposits are discovered less frequently. Deep drilling programs are expensive, and obtaining other low-cost prospects for the vertical distribution of ores is important. The Linlong goldfield comprises deposits with a total gold resource of about 1,000 tons. Much of the gold resources are in the footwall of the Potuchin Fault and hosted in Linlong biotite granite. Gold mineralization is dominated by a series of more than 13 coarse veins. We took 4 samples from the main ore bodies and their altered wall rock. The alteration is key phase forming an outer halo, and coarse pyrite sericite alteration forming an inner halo. Circle and peptide screens are from the 2 samples and conducted LA acid mass uranium lead dating and trace element analysis. Most zircon screens from key feldspar altered Linlong are anhydrous and display growth zoning, revealing a magmatic origin. They yield a weighted mean age of about 160 million years. Some greens with their dark rim of growths yet apparently young age of 125 million years. That these current overgrowths occur with mineralization. The ages of the inherited zircon show peaks of Paleoproterozoic, Neoproterozoic, and Triassic. The types of peptides are observed. Type 1 peptides from the altered Linlong granites are anhydrous and show texture indicative of fluid metabolism. They yield low intercept age of about 160 million years, which are consistent with the zircon ages, confirming that they was originally primarily magmatic. High strontium yttrium ratio and low LIEs and trend towards low-grade metamorphic and metasomatic. As a result, we propose that they are magmatic and metasomatic. Anhydrous type 2 peptides were observed in the hydrothermal coarse-vein samples. They yield lower intercept ages of to 27 million years. They are further divided into 2 subtypes. The type 2A peptides originate from S-type granites. Most type 2B peptides plot in the high-grade metamorphic field, indicating that they are mostly likely derived from high-grade metamorphic rocks. The type 2 peptides are much older than emplacement of the host granite at about 160 million years and the gold mineralization at about 120 million years. As a result, the type 2 peptide are significantly captured from rocks below the Linlong granite by hydrothermal coarse veins. Location of the unaltered peptide significantly source constrained by peptides uranium lead closer temperature, paleo surface temperature, paleo geothermal gradient, and gold mineralization paleo depth. We can infer that the source is less than 4 kilometers below sampled granite at 120 million years. So some implications. For Jiaodong Earth, the ore body extends less than 3.9 kilometers vertically relative to the simple granite at 120 million years. For mineral exploration at depth, appetite synchronous in hydrothermal wind is a low-cost and low-polluted tool for determining concealed rocks at depth. Thanks.
Those were great 3 talks, and I've learned so much, and I will make some more time to go back and just rewatch them. So now we're just going to have a short Q&A session, and the first question goes to David. David, the question reads as follows. The lithium deposits in Ireland extend north eastwards. Do they go as far as the UK? And the second part of your question, David, is which is coming from Manuel, says, what is the source and origin of the hydrothermal fluids that overprint the primary magmatic stages 1 and 2 assemblages? Is it exclusively magmatic? Over to you, David.
So yeah, for the first question, as far as I know, there haven't been found any spodumene pegmatites in Great Britain so far. But you have the tin deposits in Cornwall, and they are very lithium rich, and they have quite significant zinnwaldite, which is a tin lithium mica. And these deposits essentially share the same basement as the lithium deposits in Ireland. However, they are part of 2 different orogenies, Cornwall being formed in the late Vercin, I think. And the other one regarding the fluids, we haven't had the chance to do stable isotope studies yet. I would assume there's some interaction with the host rock and some interaction with meteoric fluids. But the whole stable isotope part will be a bit tricky because we think the pegmatites themselves are annotated melts of metasediments, and they probably have very similar isotopic signatures to their host rocks. So this is a bit tricky, and we don't know yet, or we haven't started looking into this yet. So I'm sorry, I can't really say. But I would assume most of what's going on is pegmatite-derived fluids. And so far, we haven't seen any indication that, for example, metals were derived from the host rock and then deposited in the pegmatite.
Thanks for that answer. Just a comment in there. I actually like how the 3 speakers sort of linked their talks to climate change, to ecological and societal changes. So that's that was brilliant. The last question goes to Kibone, and it's again coming from Manuel. Manuel wants to know, do the different types of pyrite indicate different mineralization stages? If so, which stage is strictly associated with the native gold? Kibone, over to you.
Thanks, Halleluya, and thanks, Manuel, as well, for your question. I think the orthogenic pyrite types are the ones that are associated with the gold, with the hydrothermal gold in particular. So the images that are included on the or on the petrography of the ore minerals, they show that the gold that you find there's gold that you find at the boundaries of the orthogenic pyrite types. So the euhedral pyrites and also on the pyrite overgrowths, you see the gold that was destabilized when the hydrothermal fluids or the gold-bearing fluids were in contact with these pyrites. And I think also it's also important to emphasize that there is detrital gold that was carried with those concentrically laminated detrital pyrites. So there's both detrital gold and hydrothermal gold, but the main one is the hydrothermal gold in the Black Reef.
Brilliant, brilliant. Thank you to the speakers, and thanks to everyone that asked a question. So we are now moving to the part 2 of the technical talks. So we're going to listen to 3 amazing speakers again, and then we'll follow the question session. So enjoy the next talks.
Hello, everyone. My name is Manuel. I'm a student at Kyushu University. Thank you so much for inviting me as I extend my congratulations to the NUI SEG Student Chapter for this wonderful initiative. I'm really pleased to share with you part of our research about understanding the evolution and origin of gold mineralization in Mozambique belt because of the Nalia, Makorongo, and Namco prospects, which are located in northeastern Mozambique. Well, before I proceed, allow me to acknowledge my supervisors and all these institutions that are supporting my study over here in Japan. Some of you might be familiar with the Mozambique belt, which is a huge tectonic unit which was formed during the collision and amalgamation of different tectonic blocks during the East African origin. And in northern Mozambique, the Mozambique belt comprises high-grade metamorphic complexes ranging from Paleoproterozoic to Neoproterozoic from west to east. And our study area is located within the Mozambique belt, but particularly in what's called the Shishano complex, this bluish unit over here, which is enlarged in figure B. And the Shishano complex is interpreted as a NEP. It's north-south trending tectonic units that is thrusted over the Marupa complex, which is Mesoproterozoic in age. And the study area comprises mainly amphibolites and gneisses, including coarse mica, gneiss, and schist also. And the host rock in the Nalia and Makorongo prospect, as we will see in the next slide, are the amphibolites, while in the Namikup and Inko prospect, the coarse mica gneisses, they host the mineralized quartz vein. Our study is motivated by the fact that there's a lack of study about gold mineralization in northeastern Mozambique. And actually, this is a problem that affects all the Mozambique belt. So we have few studies addressing issues like how these gold mineralization were formed in these very important tectonic units. As we can see from this left image over here, northern Mozambique is rich in terms of mineralization. It has different mineralization, including base metals and also precious metals. Well, that area is located around here. And our study aims to reveal the geological characteristics and or forming process of gold mineralization on the basis of geochemistry, fluid inclusion, and stable isotopes. We are also planning to conduct geochronology because this is ongoing studies. But so far, we have conducted mineral chemistry, fluid inclusion, and stable isotope study. Because of time limitation, I will present the results of the Nalia and Makorongo prospects only. And the geology of these prospects is very similar. The mineralization is associated with quartz veins, we can see in this figure, which are hosted parallel to the foliation of the host amphibolite rocks. Same in the Nalia prospect. And the host rock comprises mainly plagioclase and amphiboles as the main minerals. And in the Nalia prospect, the host rock is highly foliated. We have these amphiboles and biotite forming this leptoblast texture. While in the Makorongo prospect, the host rock shows almost massive texture with amphibole, regular amphibole and plagioclase, as we can see over here. But one important aspect that we can pick from this petrography study is that we have the host rock near the veins. It contains minerals such as amphiboles and plagioclase that are stable. We couldn't find any fresh mineral near the veins. And this has implication for the timing between the mineralization and the peak metamorphism of the host rock, because these amphiboles and plagioclase, they are peak metamorphism minerals that still preserved within the contact zone. And another aspect is the occurrence of sulfides, which are disseminated in the host rock, especially in the Makorongo prospect, And some of these sulfides, they replace amphiboles in the host rock. And this also has implication as for the timing between the mineralization and the peak metamorphism of the host rock, which hopefully we will discuss in the next slides. The ore mineralogy of these prospects is also similar. We have mainly pyrite, pedotite, and chalcopyrite, and we also have minor tellurites, especially hesite, which occur as inclusions in pyrite, and we also have gold, which was found in both prospects, and gold in the Nalia prospect occur in native forms, and in the Makorongo prospect, gold occur in electron form, which means it contains a considerable amount of silver. For the fluid inclusion study, we conduct the analysis of fluids that are hosted in coarse veins, which are mineralized coarse veins. And two types of fluid inclusions were identified, which includes the type 1 carbon dioxide one-phase inclusion and the type 2 aqueous two-phase inclusions. And these two types of inclusions, although they are contrasting in terms of composition and form, they are found coexisting in the same fluid inclusion assemblage. And the homologation temperature of the type 2 inclusions, which was used to constrain the PT condition of the mineralization, it ranged from 220 to 400 degrees Celsius for the case of the Makorongo prospect, and for the Nalia prospect, it ranged from 240 to almost 380 degrees Celsius. Sulfur isotope study was conducted on pyrite and pedotite, which are the main ore mineral in both prospects. And the sulfur isotopes, as we can see in this figure over here, it overlies different fluid sources, including metamorphic and magmatic sources. So we cannot distinguish the source of the fluid based on sulfur isotope only. And the same thing happens to the oxygen isotope, the right figure. We can see that this value, they range from 0 to almost 10, and they overlap different fluid sources, including metamorphic and also magmatic source. So we need to combine this data with other information to constrain the source of fluid inclusions. I mean, the source of the fluid. And this includes fluid inclusion results and also the tectonic sector of the study area. We constrain the PT conditions of the mineralization mainly on the basis of fluid inclusion results and also sphalerite geobarometry. Fortunately, I didn't show sphalerite geobarometry data because of time limitation, and for that you please have to believe in whatever I say. And the PT condition of the mineralization in the Nalia prospect, it ranges from 400 to 600 degrees Celsius and 300 to almost 180 megapascal. While in the Makorongo prospect, the temperature range from 300 to almost 440, and the pressure range from 200 to 150, relatively lower compared to the Nalia prospect. But to the right figure, we can see here the PT condition of the host rock peak metamorphism, which were estimated on the basis of amphiboles and plagioclase geothermal barometry. Again, I didn't show here the results of the amphiboles and plagioclase geobarometry because of time limitation. You still have to believe in whatever I say. I'm sorry for that. But we can see here that the PT conditions of the peak of metamorphism of this host rock is considerably higher than the PT conditions of the mineralization, which is shown here. So this can tell the timing between the mineralization and the PT metamorphism of the host rock, which is very important to constrain when it comes to study about gold mineralization hosted in metamorphic settings. So from this, we can rule out the hypothesis that the mineralization is seen peak metamorphism of the host rock, because if it was the case, then we should have almost the same range of pressure and temperature conditions, both for the mineralization and the PT condition of the host rock, which is not the case over here. So we conclude based on this that the mineralizing fluid in the Nali and Makorongo prospect should be aqueous carbonic fluid that could be originated by the volatilization of underlying rocks, because we cannot call upon the volatilization of those rocks that host the mineralization, because they achieved peak metamorphism probably before the mineralization. And this is also supported by the occurrence of pyrites and other sulfides replacing amphiboles in the host rock. And we thus suggest that the gold mineralization postdates the peak of metamorphism of the host rock. And the precipitation of gold could be triggered by fluid phase separation, as we saw from the fluid inclusion results. We observed aqueous inclusions and carbonic inclusions coexisting in the same fluid inclusion assembly. And this shows that these fluids, they are cogenetic, and probably they resulted from one phase, one type of fluid that was separated into these two phases, or two types of fluid inclusions. And finally, we also conclude that the gold mineralization in this process can be classified as orogenic type gold based on fluid inclusion results, stable isotopes, and the field observations. As for the contribution of our study, it's difficult to say directly its impact to the society, but we believe that based on our results, the exploration of gold can be increased in northern Mozambique, because, as I said, this is the first study to address these issues in the study area. And also we hope that from our results, the government can identify and promote those gold prospects for the for attracting investment and probably leading to mining of gold. And this may contribute to the economy of the country. That's all that I had to share with you. And thank you so much for your kind attention as I extend my congratulations and wishes of Happy Earth Day.
Welcome to my presentation. I'm Victor Bertransson Erlandsen from the Montana University in Leoben in Austria. And I will be presenting and discussing some of my PhD results concerning trace elements and the applications that you can basically use trace elements for when constraining or forming processes and so on, based on my Namibian sediment-hosted copper cobalt deposit of my PhD research. This is together with the Gecko Namibia, an exploration company that supplied us with drill cores and help in the field. But first of all, why do we care about trace elements? I think first of all, we need, of course, to signify the cobalt, the trace element in this case, but the reason for this, the interest in this occurrence for green transition and electrical batteries and so on. But furthermore, sulfides deposits such as this one and deposits in general can contain significant amounts of gallium, germanium, indium, and other critical raw elements, materials. And basically, if these trace elements are hopefully not even the trace elements, but these critical raw materials occur in high enough concentrations in the ore, the whole economic value of the ore might be increased. And we've seen this in some of my work I've done together with a colleague on the Kupy schiefer, a sediment-hosted copper in Poland. We see some very nice germanium and indium values. But furthermore, I think a lot of projects are being started right now, basically focusing, at least here in Europe, on either revisiting old mines or even occurrences that weren't economic first and reevaluating them based on the composition or component of critical elements in them. But what I will also focus more on this in this presentation is the genetic interpretation that we can do from trace element data to constrain, for example, formation conditions. My deposit or mineralization is the Dollison ore formation in northwestern Namibia. It's located right here in the Kauko belt, which is the northern branch of the Damaran orogenic belt. And it's more or less a anomaly or enrichment in copper, cobalt, zinc, nickel, iron, and magnesium. And was first explored already in 2013, so not too far long ago. So it's pretty new. As I said, situated in the Kauko belt of the Doran origin, hosted Neoprecursor calcareous siltstones mostly, siltstones, dolomites, even some anchorites. So it's a very iron-rich system, basically. That's what we're working with in the Damaran supergroup. And this whole, both the setting and the sediments are coeval and basically an analog to the Central African copper belt, where we get our cobalt from. And it's good because there has not really been much work done on this mineralization or in this area, really, to be honest. So we kind of use the Central African copper belt as kind of a reference and analog to work with. And the mineralization styles that we've been analyzing of the DOF deposit in general, we have the disseminations, usually monosulfides disseminated within the host rock, bit coarser as you can see, some, and some are more fine-grained. We have clusters, usually occurring with polysulfides, so a lot of sulfides, pyrites and sphalerite, you'll see this as well. But also within the host rock, we have nodules, partially mineralized and sometimes completely mineralized. The so-called sigma, as I've just briefly called it or named it, and it's first when we did the drill core logging, we did consider this being a nodule, but when we actually make sections, you see nice pressure shadows and pressure wings, basically, like it's sigma class. We have a lot of veins, quartz carbonate dominated, quartz dominated, sulfide, veinlets, veins, throughout the stratigraphy, of course, as well, but it's a major component. And then we have the last type of mineralization style, which are these so-called events. The company interpreted them first as being slump structures due to their ductile appearance, as they do have a ductile component, but also some brittle. These are pretty enigmatic still, and we do not really understand what they are, if they're primary, secondary, if they relate to mineralization, as they are also found in the stratigraphy unmineralized. I have been wondering if these are some type of perhaps crack seal veins, but we're still working on really understanding these. So the sulfides we have in this mineralization is sphalerite, chalco, pyrite, lineite, which is the major cobalt sulfide, pyrite and pyrotype, and then some accessory galena and cobaltite. And sphalerite, chalco, pyrite, and pyrotype are the ones that I've been focusing on with the laser ablation ICP-MS. And this is basically what it looks like. Here we see one of these clusters mineralization styles, where we have the lineite being surrounded in a matrix of pyrite with some interstitially grown chalcopyrite and sphalerite. And then here we see the black craters, beautiful round craters from the laser ablation ICP-MS. So let's look at some geochemistry. Here we have sphalerite geochemistry of 4 selected elements. They are here split up according to the mineralization styles that we looked through. And I hope you agree with me that you can basically see a trend of the green and the purple one, the sigma and the veins, clustering together, and if not together, at least separated from the rest, which are the disseminations, the clusters, the nodules, and the events. And as you can see, they're not always that one group of mineralization styles are enriched compared to the other, but they are enriched and depleted relatively to each other, and it varies which one is the more enriched group, so to say. but I think you can agree that there seems to be a nice grouping at least. And the same is seen in chalcopyrite. I mean, now I'm just showing a few of the elements, but this rings true for more elements that we've been analyzing. And in some elements, of course, we don't see any grouping and they can be completely scattered. But we see this in many of the elements for both sphalerite and chalcopyrite. And I mean, it looks very clean and nice grouping, basically. When it comes to pyrite, it is not as clear. I have only shown two here because basically there is not much to say with the grouping. Perhaps the only thing you can say is that there's cluster and nodules grouping together. This is probably the only real trend we can see. Do note that there is no dissemination in this of pyrite. Disseminated pyrite do occur outside the ore horizons in the host rock as rhomboidal pyrite and also euhedral, probably metamorphic pyrite, but not within the main ore horizon. So one of the nice things that you can do with trace elements for a lot of minerals is you can plot them in all these different kinds of plot, and you can discriminate where the origins of the fluids or the ore forming processes come from. This might be one of the first examples from Cambial and Ether on the pyrite and pyrrhotite, where you plot nickel and cobalt to see basically if it's magmatic, sedimentary, or volcanic. And I think this one signifies and really shows my problem, that my data really plots in the middle of nowhere for basically all of them, all of these discrimination plots that have been produced. Of course, Campiel and Ether already pointed out that when you are in a area or metallogenic region, which is cobalt or nickel rich, this plot actually doesn't work. So even from the start, we already can say that this one doesn't work, but it really shows that we just plot out of nowhere, and this rings true for a lot of, or basically all of discriminations plots that I've tried to apply, which is very sad because this is one of the great things that you can really do with trace element theta. But Fretzel et al. 2016 published these calculations to use the GGIMF sphalerite geothermometer, which is germanium, gallium, indium, manganese, and iron composition of sphalerite to calculate the formation temperatures, which I did here. And I mean, we can see that it's somewhere between maybe 320 up to 410 almost. Not too bad. It's a big spread, but unfortunately, this whole system has a closing temperature of 310 plus minus 50, really showing that we can't even use this one either. All we can say that the sphalerites from all mineralization styles formed above this 310 plus minus 50. So what does all of this non-data or really add up to? Well, I do think that you can really see a grouping of the mineralization styles, and I hope you guys agree, at least for the sphalerite and chalcopyrite. And I think this really shows that trace elements can also be applied to kind of suggest or indicate generations that, you know, if they have such a similar signature in the trace elements, it is, I argue, very plausible they formed during the same event or mineralization stage. And this is something that, you know, traditional or conventional paragenetic investigations using microscopes really can't prove. When we compare in the events, we have pyrite and coexistent pyrrhotite, and basically we see elements such as copper, arsenic, and lead being depleted, while cobalt, nickel, and selenium is basically remains the same. And this is a typical thing for metamorphic in green schist amphibolite facies pyrite, where pyrite will liberate copper and lead and such, and these will form other phases, which we see with this sphalerite and chalcopyrite, while cobalt, nickel, selenium, which is tightly bound within the matrix or the crystal lattice, remain in the iron sulfides. The sphalerite also, I mean, really shows we have a higher temperature, so 310 at least. And I think all of this really shows that we have a metamorphic overprint or affinity of the mineralization. And the grouping shows it's a multi-stage origin. And I kind of suggests that we have these primary pyrites, green schist facies is happening. They're liberating lead and zinc, and copper, producing this chalcopyrite sphalerite. The recrystallized iron sulfides still remain with the cobalt and nickel and selenium, which we see. But of course, these sedimentose coppers are very, a lot of people want to see them as early diagenetic or such. And of course, we can't really prove that there is not, if it's been metamorphically overprinted. As I said, there is framboidal pyrite and metamorphic pyrite in the host rock as well. And this is something I want to investigate for the future. And that was everything for me. Thank you very much.
Hello everyone. My name is Aileen and I'm currently a researcher based over in Ireland with UCD and ICRAG, but I'm also the chair of the Equality, Diversity and Inclusion in Geoscience Initiative, or EDIG. So for the next couple of minutes, I just want to talk to you a little bit more about EDIG in terms of our background, who we are and where we came from, and also our plans. EDIG is made up of volunteers who wanted to learn more about the challenges experienced by other geoscientists related to EDI topics. So originally, EDIG started off as a suggestion for a workshop on unconscious bias for our own research centre after several of us experienced sexual harassment at a large international conference. And so since the last year has moved to a virtual landscape, we saw it as a pretty good opportunity to expand outside of our own research centre and include more people in these conversations. In line with that, we decided to run a free virtual conference and workshop open to everyone. So this event was originally intended to focus on gender-based discrimination, as that's where the majority of our own experience lay. But over the past year, there have been some fantastic online initiatives aimed at challenging our own ideas of what a geologist looks like, and also highlighting the barriers many minoritized geoscientists face. So as we continued our own learning journey, we realized that these challenges are often much more complex and often need to be discussed together. In line with this, we decided to broaden the focus of our conference to include more than just gender-based issues. And while we were planning, we found that there wasn't really a lot of information readily available that discusses these topics together from an intersectional lens, with events focusing on usually just one aspect. So to help us better understand how to approach and discuss these issues, we decided to run a survey asking people about their own experiences, or lack of, with EDI-related topics. So this survey was launched in the summer of 2020 and it received a really great response with 708 participants from 58 countries. And so while the main purpose of this survey was to inform the conference and to learn more about the challenges experienced by geoscientists, we now have a really great resource that we're planning to publish as a report quite shortly. So using the results, we were able to summarize the main trends from the dataset, and we're able to use these to decide on talk topics for each of the sessions for our conference. So the EDIG conference ran over 2 days in December 2020, and we had over 700 registrants for the event. And we also had 14 supporting partners that are outlined on the side of this page, who helped share information about the event and the survey, really helping to boost awareness of our events. So the main body of the conference was split into 3 sessions, focusing on the themes of where have we come from, where are we now, and where are we going, finishing up on a workshop on unconscious bias. So primarily, we wanted to try and provide a platform for learning for ourselves and the wider geoscience community, to help us all come together to make geosciences as inclusive and accessible as it can be. Over the course of the conference, we heard about how much we have progressed, but also how there is still quite a lot to do. And we also heard from several geoscientists on the challenges and barriers to entry and retention, who shared their own personal journeys with us. And we heard a lot of suggestions about how we can all be allies, we can all be supportive, and we can all do something, and how it's really all of our responsibility to take part in these conversations and these actions. The conference really highlighted how complex and intersectional these topics can be, and how many minoritized geoscientists are often excluded from conversations due to this intersectionality. So you can actually rewatch the EDIG conference on our YouTube channel, EDIG conference. Most of the recordings are available there, including of our survey results by Dr. Jess Franklin from the EDI committee. While EDIG was originally planned as a standalone conference, from the conversations that took place before, during and after the EDIG conference, We saw there is still a need for events and projects like EDIG, and so we've been restructuring and rethinking the focus of the project over the last few months, and we plan to update everyone on this pretty soon. In line with that, we were planning on changing our name from Equality, Diversity and Inclusion in Geosciences to Equity, Diversity and Inclusion in Geosciences. This is mostly in response to several conversations we had with lots of different people and different initiatives, and so we feel equity is more representative of what we want to actually achieve. So moving forward, we want EDIG to act as a platform where different geoscience groups and geoscientists from all backgrounds can come together to discuss, learn about, and promote progressive action within geosciences to help make our community as inclusive, accessible, and equitable as it can be. So in line with that, we'll be focusing on events, networks, resources, and research. And to correspond with this, we're going to develop a website to collect all of these resources and different bits of information that we plan to launch. This is still in the planning stages, but we're hoping to update everyone on this, our updates and plans quite shortly. So moving on from that, there's lots of other ways that you can get involved with EDI in geosciences. And so I'm just going to mention that if you want to get involved with the EDIG project, we'd love to hear from you, and you can reach us on our email on the slide here, or you can follow us on social media. But there's a lot of other groups that are really active as well in terms of EDI, and they have a lot of really great resources and support and networks that you can join in with. And so we've listed a couple of here, and you can also see all of our supporting partners for the EDI conference on the side. But I highly suggest checking out their web pages and seeing what they offer as well, because there's some really lovely communities that you can join here. So there's lots of other resources you can take advantage of, like different podcasts or blog posts and webinars. And just a reminder that the EDIG conference is up on YouTube and you can watch it in your own time. And so I'm just going to finish there, and I just wanted to say thank you so much for listening, and if you have any questions, please reach out.
All right, we are at the end of the part 2 of the technical talk, and we are now moving on to the question and answer session. And just a comment there, we are actually, this is brilliant, linking research to, or bringing EDI issues to research, because I really think for us to do great work, for us to do great research, we need to address all these EDI issues. So thanks to the speakers for the brilliant talks. The first question goes to Manuel. Manuel, the question is from Sibru, and he wants to know that, he says, thanks for the great talk. What hydrothermal alteration minerals do you see associated with the gold mineralization? Manuel, over to you.
Thank you for the question. Well, we didn't find mineral alteration minerals. Of course, we expected carbonate minerals and also some iron clay minerals, but unfortunately we didn't find, and that brought us to the conclusion that the fluid didn't react with the rock that much, and rather it was just passing through the foliations and crystallizing the gold. Thank you.
Thanks for that question. Victor, there are 2 questions for you, Victor, here. The first one is from Philippa, and she wants to know, I'm not sure if I missed it, but do you assign each of the different mineralization type to a specific origin? If yes, how do you explain, and which is the process behind the similar trace element signature of the chalcopyrite and the sphalerite in the sigma and the veins? So Victor, do answer the first question, and then I will say out the second question.
Yeah, thanks. Yeah, so I mean, I could talk about this for easily an hour, but I don't think I pointed this out due to the time, but more or less, this is my kind of working hypothesis, that we saw these at least 2 distinct groupings, and I kind of want to argue that they are at least showing that there is, 2 different events forming these sulfides to the specific origins. I am kind of still in the working progress of that, trying to actually figure out when and what and where and so on. But I mean, basically, yeah, what I'm saying is that the chalco and the sphallies would form together, and we see it a lot. There's a lot of interstitial growth, and they're basically going hand in hand in a lot of cases. When it comes to the sigma and the vein, I'm kind of working, or like playing around with the idea that maybe it's like a later event. There's some trace element data that kind of suggests it's a lower temperature of formation and something is going on, and you're basically towards the end of the Damaran origin, you're getting some recrystallization, basically forming these veins and also these this sigma. I think that kind of answered it.
Brilliant, brilliant. The other question for you, it's from Manuel. He's saying, thanks for the talk, Victor. I didn't know much about sphalerite thermometer, but now after watching your talk, know that your talk now that in my apply, okay, you probably is going to apply that in his studies. So his question is, it's rather a suggestion to sort of say you have sphalerite coexisting with pyrite and pyrrhotite, right? It might be worthwhile to apply sphalerite geobarometry based on the pyrite content, as the sulfur activity was buffered by the both iron sulfide. So it's not a question, but rather a comment for you, Victor.
Yeah, I appreciate this, Manuel. And I was relatively recently enlightened about this sphalerite geobarometer. So it is something I'm considering, or at least I will consider, to get some barometer. Because I mean, I tried this thermometer. It's just like, nah, we're not gonna be working for you. But getting some pressures would be pretty great as well. We are working on a multi method to get at least the temperature of this whole region or the area. But yeah, thanks, Manuel. I will consider this.
All right.
Thanks, Philippa, for your interest.
That brings us to the end of part 1 of Technical Talks. Just to thank all the speakers for the contribution, and just to thank whoever contributed, be it in terms of asking questions or comment. This symposium is really for us to learn, to listen, engage, and I'm really seeing already people engaging with each other, asking questions, and also giving ideas on how they could tackle their research. Continue doing that in the chat box, and then we'll move on to an interesting part 2, and we are going to listen at the perspective video that we have received from geologists from all over the world. And please just note that we weren't able to play all of them, but we've placed all the videos that we've received on our YouTube channel, and that is going to be shared in the chat. So enjoy.
I want to become an economic geologist because I believe we are absolutely essential in order for the world as a whole to move towards a more sustainable way of living.
Geology is ruling pretty much where all of our natural resources are coming from.
The path to sustainable development is lined with minerals.
Lately, new technologies like solar panels, electric vehicles, communications, need a lot of elements that we are not used years ago, like gallium, germanium, niobium, tantalum, rare earth elements.
Elements like lithium, copper, cobalt, and zinc are vital for the development of environment-friendly technology, and they can only be obtained through mining and exploration of new ore deposits.
I am really interested in economic geology because I think it's key for the development of countries.
Economic geology is actually the branch of geology that considers a lot of factors in terms of removing minerals from the ground. So you would look at your environmental, your political, your economic, and your social factors, and consider whether removing that material is actually worthwhile.
Of course, it also helps with the development of the areas around the mines, and also the taxes that go back to the government so they can invest to solve other issues.
Locating and extracting geological resources are vital to tax revenues and economic growth.
Very important is for us as geoscientists to contribute to their discovery and their recovery in the most responsible way and sustainable way that is possible.
Whether this is finding greener methods of extraction or reducing the chemical footprint that the mining industry has.
We need to be able to extract these metals in a green and non-invasive way to no longer scar the earth.
And mining companies are becoming a lot more socially responsible, but I would like to continue pushing that responsibility and ensuring that wherever we mine, the people who live there and live near there are really well looked after and that they benefit from the mine just as much as the world does from extracting those metals and materials.
In countries like Germany, you have very advanced mine reclamation systems, and that's something I want to implement in my country. This shouldn't just be done after. This is something that should be implemented before a mine is even constructed, so that land is assured, it's assured to succeed or thrive after people are done mining in that area.
Economic geologists should make their due contribution for this.
We as economic geologists will need to be up to the task to basically extract and produce metal in a more sustainable way.
We need to make sure that we are helping people understand not only where, but how we extract the metals that they use every single day in their routine lives. So there's an opportunity for us to maybe go back to a school or a university and give a talk, giving our experiences of what the industry is actually like, or even just having conversations with family and friends.
As an industry, we need to continue to improve safety for our people. And we need to become increasingly socially and environmentally responsible.
As a field geologist, perhaps we will be the first one into a new project or into a territory, and we will need to be aware about the principles and guidelines for protecting the environment, for early community engagement, and at the same time working responsible in a safer way than before.
Now, geological knowledge itself is quite important, and it's not only important in the extraction, but it has multiple end uses as well. Land use planning, environmental monitoring, water abstraction, and construction are just some of the many uses.
This means it's a very important time for us geologists to share our knowledge and participate in the decisions being made about our resources and any other possible uses of the subsurface to tackle the big environmental challenges that we're currently facing.
And I believe that through innovation, through new ideas and new technologies and new processes, we can go a long way to improving and optimizing our industry. But this all requires diverse teams of really skilled and intelligent and really open-minded people.
If you ask me, I say our generation of early career professionals and students are well up to the challenge. In fact, I dare to say that we're motivated by this challenge.
And so for me, there cannot be truly any sustainable development without geology and geological knowledge.
I want to become an
All right, I hope you guys have enjoyed that as much as I've enjoyed it. And thanks to everyone that contributed. And just to sort of mention that again, please do visit our YouTube channel. All the other videos we received from all over the world are available, and you can always watch them at a later stage. So we're now moving to the last part of this session 1, which is the panel discussion. And I would just like to please ask our panelists to unmute and turn on their cameras if that's possible. So the first panelists are Dr. Lingley Zhou, Manuel Niob, Josephine Ushona, Rose Clegg, and John Barry. Please unmute your mics and turn on your cameras if that is okay. Are we all there?
Yes. Yes.
Perfect. So today, just the panel discussion we're going to have today is to really just tackle issues that around climate change, around ecological and societal changes that we are experiencing. And we've divided it in a way that we're going to first sort of look at sustainability, environment, circular economy, and critical minerals. And then we're going to look at social responsibilities, and then we will move into public perception, and then we'll conclude with training and mentoring and career advice. But before we delve into the discussion, I would like to ask our panelists, I'm going to give you each 60 seconds to tell a story about yourself, 60 seconds. And I'd like to start with Dr. Lingley.
Okay, thanks, Halleluya, and thanks for the SEG chapter, really amazing initiatives. So I am Ling Li. I'm a research fellow at the moment working with ICRAC and UCD University College Dublin. My research mostly focusing on understanding the formation process of critical mineral resources through Earth's evolution. And my research has been covering carbonatite rare earths and orogenic gold and also sedimentary system, porphyry systems. So I'm really look forward actually to chat all these varieties of resources with everybody and how it can sustain the supply of the society.
Brilliant, brilliant. Manuel, over to you.
Thank you, Halleluya. My name is Manuel and I'm a PhD candidate at Cuse University. My research is focused mostly in orogenic gold, for the inclusion of geochemistry of these gold type deposits. And I've been also working with some professors that are focused on resources in social sciences. And that's all probably for me.
Perfect, perfect. Rose, over to you. 60 seconds.
Thanks, Halleluya. So yeah, I'm Rose. I'm a PhD student at the University of Leicester studying alkalic type epithermal mineralisation of tellurium and gold in Fiji. But I also do a lot of outreach aimed at encouraging underrepresented groups to study geology. And last year I co-founded Responsible Raw Materials, which is a not-for-profit aimed at improving sustainability in the raw materials sector.
Brilliant to see young people involved in a lot of this sustainable development link stuff. Over to you, John. John Barry, over to you.
Yes, well, thank you very much for the invitation and congratulations on putting this wonderful symposium together on Earth Day. I've spent the last 30 years in exploration around the world, exploration geologist. I'm a SEG fellow, but today my hat that I'm wearing is spokesperson for the Institute of Geologists of Ireland. We've recently published fact sheets on the industry, mining and our green future, and also the value of mineral exploration. And we see this as important because right now we have groups that are trying to put forward, obviously, the idea of a green energy future, sustainable future, but in many cases are opposed to mining. And it's how we join these things up in the future, which is going to become very important, and it must be fact-based and science-based. And that's why we've come out with these fact sheets. So thank you very much for the invitation.
Well, thanks for accepting our invitation, John. And it's good to know that we do have some experience in the room. So we are looking forward to sort of drinking from your cup of your experience. Josephine, over to you.
Yes, thank you so much for the opportunity, Halleluya. My name is Josephine Ushona. I'm a senior geoscientist at the Ministry of Mines and Energy under the Geological Survey of Namibia. I'm actively involved in science outreach programs. We try to raise awareness on the importance of science, specifically earth sciences. I'm the General Secretary for YES Network and a country representative of the YES Network National Chapter.
Brilliant, brilliant, brilliant. Just for the audience, please feel free to drop your questions in the chat as we move along with our panel discussion. So this is really just to start the conversation because currently all the talks are around sustainable development. So my question to the panelists is, what does sustainable development means to you? And what do you think are the key fundamentals in achieving this? And I'd like to start with John.
Okay, well, it's kind of interesting. A mine is not sustainable because it depletes its resource from day one. So for our industry to find these critical metals that we're going to need going forward, I mean, you know, we just look at the amount of copper that's going to be required in EV metals. There was talks on lithium and the impact on the environment and so on. We're going to have to find small planets of metals, and that means exploration. So I think it's an incredibly exciting time to be a young economic geologist. I think it's this huge transformation that's occurring in our society. Sustainability, look, mining is invasive. It is an invasive industry, and we need to use all the technology and the knowledge that we have. The world has changed hugely in the last 15 years in terms of regulation and compliance and that. and we need to just mitigate that impact. We need to reduce it as much as possible. But ultimately, sustainability of our mining is going to revolve around exploration, discovery, and then the recovery of these metals, which is also a huge part of it. Our mineral processing, how we get better at doing that. Often mining critical rare metals, which are in very small quantities in rocks. We have to mine large tonnages of these rocks. So it's a challenge. It's a challenge, and it's a balancing of cost benefit going forward. That's all I would really say at this point. It's a huge subject, right?
Brilliant for that answer, John. And you mentioned critical metals or critical minerals, and this is where I would like to bring in Lingley and Rose, because they're also interested in critical metals. And Lingley, you are busy working on one of these research that involves critical metal. Can you please sort of just take us through what this has to do with sustainable development and how you think it's going to be achieved? And then Rose can come through as well.
Yes, I think it's a very good continuation with what John just mentioned in terms of sustainable development. As probably many of us are aware of that, it includes three parts: the social impact and the environmental impact, and also the economic impact. That's the classical three aspects. But I think nowadays it comes to more and more discussion, or more the fourth dimension. It is the security of the critical raw materials. And that is really my past 6 years postdoc research focusing on how to sustainable to secure these critical metals, and in terms of recycling as well for the mine tailings. That comes to a lot of the topic nowadays, circular economies. And I think from this part, I can really nicely pass it to Rose.
Yeah, thank you. I mean, in terms of critical metals, by definition, we don't have security of supply of them, and we do need them in terms of going through the green transition. But I think it's also really important when considering sustainable development to remember that whilst this is quite a trendy topic, because people are very happy to talk about renewable energy, we don't have houses or roads or glasses to drink water from without mining either. And mining is essential to any of the sustainable development goals, whilst being an unsustainable industry, because by definition, you're taking something that you can't put back. And research into how to do this properly or effectively environmentally is really important, because at the minute there isn't enough metal in circulation to rely entirely on recycling or entirely on a circular economy. And this is something that I think this is where the public perspective thing comes in, because so many people don't realize that the volume that we need, we can't just rely on recycling.
Brilliant, great talks there. But before I get to Josephine and Manuel, I would like to sort of post a question to Lingley, Rose, John, and Josephine and Manuel, feel free to jump in. But this is coming from more the academic stuff. So it says, academic fundamentals and applied research is essential for sustainable development. And we know that, especially in mining and finding new mineral deposits. A major proportion of the research work is carried out by postgraduate students and early career individuals. So do you think this is sufficiently valued and recognized by the industry or by the society or even by academia itself? If not, how do we think we can improve this aspect? Anyone feel free to jump in.
Well, I would like to.
No, you can go ahead.
Okay, thank you. Well, I think that the work that geoscientists they do, somehow it's not valued, especially for those non-expert people, and that's understandable because of the language that we use in most of our works. It's not compatible with the educational background of other people outside geoscientist family. And that's also linked with what I think it is the president-elected of SEG said, like the way we communicate, it's really important so that our work can be valued. And that brings me to the final question, which is how can this be changed? Then I think we have to make sure to bring down our narrative to those who are not geoscientists. That way, we may make sure our work can be valued for those who are not geologists, especially social and politicians. I would say that. Thank you.
Brilliant, Manuel. Josephine, you wanted to add to that? Please, you next.
Yeah, I think, John here, I think that the last year of COVID around the world has shown how the general public can suddenly get very, very interested in science. And we're surrounded by people having views of these things. So I think we need to reach out and engage and educate. And it's not just about the what and the where, it's also about why we're doing what we're doing. I mean, someone called it the revenge of the geologists, that we're finally, we're going to come to the fore here. I mean, this is an incredibly exciting time that we need to connect up to save our planet, sustainability, and the decarbonization of the planet critically with these metals. And where do they come from? All the different things that we use, from our iPhones to our computers, but most importantly, our wind turbines, our solar panels, all these things. And we need to go out and engage, and we need to communicate clearly. And I think it will happen. But we've got to maybe come down from our ivory towers and get out there on the ground and engage. And each one of us is an ambassador for our science and for our careers.
Amazing. And we are ambassadors for planet Earth, and we need to do our part. Josephine, what is your take on that question?
Yes, I think just like any other profession right now, they're thinking that we are not heard, they don't understand the importance of what we do, be it you are a lawyer or you are an earth scientist or any other profession, but it's up to us as geoscientists to educate and inform the public out there on the importance of our services or what we do. So people don't know because they are not exposed to it. They don't know the benefits of it. They would sit, they're in a home, but they don't know why the television is on and why they are using their phones. So I think it's up to us to create that platform to include the community and engage with them on the importance of what we do, the work that we do, but on a very basic and understandable, relatable platform in an environment that they can understand.
Brilliant, brilliant, brilliant. I would like to bring in Ross in this discussion because of what you have co-founded, the non-profitable organization aimed to raise awareness on sustainable development. So we know that a lot of mining companies, and I'm sure you probably do have a lot of links to mining companies or mining communities. So many companies have declared a commitment to carbon neutrality by certain dates in the future, right? So do you think, how can we determine whether this is real intention and whether this is just a greenwashing? And how do we who is held accountable for these things that are being put in place?
Yeah, I mean, this is probably an unpopular opinion, but I would suggest that unless you are embedding carbon neutrality properly into ESG, it is by definition greenwashing, because you can power your mine with a solar panel, but if you've pulled all those elements out of the ground in an area which is, suffering drought, and you have really abused the local communities, then you are not a sustainable mining company, irrespective of how you are powering your mine or whether you are carbon neutral or not. That said, carbon neutrality is obviously, a great target and a great aim if it is done properly. And I'm not saying we shouldn't try and be carbon neutral at all. We absolutely should. It just needs to be done properly. And I think a lot of mining companies and investors are starting to realise this now. So whilst there is frameworks like TCFD that focus on carbon, you're starting to see a lot more frameworks coming in that consider things like biodiversity more. and other bits as well. And in terms of holding them accountable, you know, there are international bodies, there are people like, you know, the mining codes and standards and things like this are slowly coming into the mining codes. And there's frameworks, you know, that people have to sign up to, whether they be, you know, mining specific or more general, like the Equator Principles. But on a very fundamental level, I think the general public are having more say in this now, because in terms of, like, when you look at the DRC and cobalt, you know, Apple and Tesla and companies like that had a massive issue on their hands when the public started to see or images started coming out of what was happening there. And I think consumers will soon have more power to decide, you know, where their money goes.
Brilliant, Rose, for that overview opinion on the question. Lintley, you are working currently on critical, sort of trying circular economy or critical circular economy aspect. What sort of steps do we have to take to make sure that we work together to mitigate negative environmental impacts of our work? And I'm sure this links into what you're trying to do with your current projects.
Yes, I think it's in terms of minimize the negative impact of the exploration work from the mining activity, particularly. What we researchers can do in contributing to the sustainable goal. I think one of our previous talks from Houghton, from the China University of Geosciences, he gave quite a good example to use some mineral geochemistry as an indicator or vector of the how the fertilities, and if it expand that picture, you can actually use mineral geochemistries as well to compare some fertile rocks which contain those mineralization, to compare it with those rocks that doesn't have those mineralization. And by bringing a statistic approach, you will be able to actually have a quite good understandings where to target for. And that is really low cost and very low footprint as well. So that's what I see what researchers can contribute and the key steps can take to contribute to the sustainable goal in the future, but definitely in collaboration with or in cooperation with a lot of other techniques, expertise like statistics.
Thanks, Lindsay, for that. And a lot of you mentioned engagement, communication, and public perception, right? How can we effectively promote sustainable engagement within communities? John, I think I would like to get from your experience of years you've worked in different parts of the world. So how can we effectively communicate and make sure people are at the same level as the geoscientists?
Right, so I mean, people call it the social license to operate. In the early part of my career, exploration companies went out, they made discoveries. They only engaged with the public at the time where they were looking to develop those projects. That just won't work anymore. It shouldn't work. The first representative of the company to go on a site is an exploration geologist, often quite young exploration geologists, and they're the first touch points with the community. The community needs to be brought in as a partner. Their trust needs to be built. Really, we use the term, you've got to build a project, into the fabric of the local community. Because if you don't get that buy-in from your local community, you're not going to develop the project. So much earlier engagement, much more dialogue. And if you don't know something, you say you don't know something. You don't try and, excuse the word, bullshit. You say, we're doing the research, we're trying to find out the answers, and we will go on that journey with you. It's become a huge developing thing in the last 15 years, and it's improved a lot. The mining industry has improved a lot in that regard. There's still some huge issues. I mean, we saw what happened with Rio Tinto in Australia very recently, archaeological sites being dug up. So we do have some slippage. I would just say very quickly on Rose's point about ESG, we are now seeing that major funds, financial funds, are only going to invest in companies that are ESG compatible. So the investors are driving the funds to develop their investment policies. So we're seeing huge changes there as well. That's about it.
Brilliant, brilliant. I like that you touched on trust, because 2 years ago I was lucky enough to attend the Restore Summer School in Dublin, and one of the topics or the challenges that we're faced with actually involved around community engagement, ethical sourcing of raw materials, public perception, and circular economy. So through that, we sort of determined or came to a conclusion that engagement should be a process, a continuous process, and you need values to understand the sort of people you're dealing with. So it's just interesting to see that everyone understands that it's really key to make sure you value, you make people, you establish the trust which should not be broken, and you need to continuously engage from the beginning of the project, mid-project, until the end. Manuel, you were part of the Restore Summer School. What are your thoughts on this subject?
Yeah, that's really good discussion, and thank you, John, for your contribution. Well, I think to get people engaged, we don't only have to communicate them about the benefit of the mining. We have, above all, we have to know the values of those people, what they value the most. Some of them, they have what some researchers, they call egoistic values, like they want to see their lifestyle level increasing or going up. So knowing their values, we can communicate them in the way that our communication, our narrative match their values. Our narrative match what they want, what they would like to see improving. I'll just bring a quick example from what happened in my country, in Mozambique. We have artisanal mining, which started sooner before large-scale mining came. And those communities, they live on the base of those artisanal mining activities. And sometimes what happens, like the large-scale company, they come and then they get license. I mean, they license from the government to explore in that area, and that in that way, the community should leave the area. And sometimes the community have their values, which are to see their life increasing. And if the company comes to explore that area and brings a narrative that goes to their value, not only just replace them to another place, maybe we can have engagement of these people. And engagement may mean, in this case, having these people in all processes, Halleluya said, and that would be very interesting, I think. Thank you.
Interesting. Yes, we have now established that, Josephine, I'll come back to you now. We've established that community engagement is critical, right? And we have different places. We have Africa, we have Europe, we have America, we have different continents. So I'd like to hear from the speakers different ways of communicating based on your experiences as to where you're based. Lincoln, you have experience from Ireland, China, and everywhere else. Josephine, you have experiences in Africa. Rose, you have been in the UK, you have done your work in Fiji. And John, you have worked in Ireland, you've been in Africa. So I'd like to sort of hear your experiences when it comes to communication in different places you've worked on. Josephine, up next. You are the first one on the line.
Okay. I just really wanted to add on what John and Manuel said. It's very important that communication to society starts at the very beginning of the exploration program. And not only we can communicate, but we need to know how to communicate with these people. So we need to know how to communicate effectively. We should study the environment. We should study most especially the cultural differences that we have of these people in certain areas. My experience in the African Namibian context is if there's a project an exploration project, communication directly to the community doesn't really work as effective. So you should study the environment. You should know, is there a chief? Is there someone who is in charge of this community? How do I approach this chief? How do I come to him? So you need to take into account traditional aspect of it, cultural aspect of it, and you go through it. So when you you have that mutual respect, like John and yourself and Manuel said, and you really put in the effort on communicating through the different channels, then it's most likely that you are able to build that trust, you're able to build that relationship that will start on the onset of the exploration project till the ending of the exploration project.
All right, over to you, Lingley. What do you think? What are your opinions on this?
So my experience with, I just talk about my examples, my own experience actually engaged in China and in Ireland in terms of communicating with mining company as a researcher. So in China, it's some of the mines, we're talking about national culture difference, but I think within a nation, there is still culture difference from region to region. So for instance, if you go to some region of the mines, it's female sometimes are not very welcome. So at the beginning of the field trip, you really need to communicate well to make sure how to make the best arrangement. So that is my feeling of communication. But while in Ireland, my feeling is, especially in terms of big mining companies, they do have their own rules or doing things, arrange things. So first, of course, you have to respect these rules, and then see how the companies can accommodate your research demand and how you can cooperate to reach the maximum to bring benefits to both. Well, first, I think the communication is really what you want to achieve. You ask mining company what you want to achieve, what you want to understand, how we can help you. That's I think it's very important in terms of collaborations and communications.
Lovely, and I like that we are talking about collaboration and talking about engagement. Rose, you have done work in Fiji, and I believe you're based in the UK. How have your experiences been, and how is the public acceptance when it comes to the exploration and mining sector in general?
Yeah, I think to build on what everybody else has said, it's so example specific that it's hard to generalize and say one way of communication or outreach works, even on the country scale. You know, going out and doing field work in Fiji, over there, the mining industry and the local populations they work very well together. You know, there are villages that are only there because of a mine, and they have schools and they have, you know, churches and things that are important to them because of the mine, and it works really well. As a researcher going out there, you know, that there are some people who still aren't convinced that a woman down a mine isn't bad luck. And it's important to realise that things like this, you know, you have to respect that opinion, because you can't go in, because then you're just going to get nowhere. And you can't generalise. I think within the UK, you can't even generalise across, you know, different across areas. So I grew up in quite a rough area, and no one had any idea or understood why I was going and doing a PhD, even though I tried to explain the applications of it, because people just didn't understand it. You know, people in Fiji who you might think might be more averse to it or less understanding, actually far more and far better understand the benefits of mining. And I think there's sometimes a lot of arrogance that comes out of the UK or Europe in how we think we are perceived or our knowledge. And in terms of really educating people, I think geology really misses a trick, because it's such an applied science that we shouldn't just be talking to people when they're, you know, adults. Geology is a great way of showcasing science to children on a very basic, fundamental level that I think we've just missed a complete trick.
I totally agree with you, Rose. We get to hear geology as you move to university, and I think there's really that gap. I think we need to work on a curriculum that involves us giving geology, because I believe the desire for someone to learn and appreciate something should be instilled at the very inception of their primary education. And I think that's really something that is lacking in a lot of our curriculum. John, with your vast experience, how has this been to you? And what do you think can be done for us to effectively engage and communicate and make sure that people value geosciences in general?
Yeah, I've worked on 5 continents. I would say that I'm not sure there's a fundamental difference, really. People are the same, I think, around the world, really. Yes, there are differences in protocols and culture and so on like that. But to my mind, it's like if you're coming into somebody's area and it's almost like coming into their home, and you need to introduce yourself, you need to build some sort of level of comfort and trust with these people, and be trustworthy. As Joycey was saying, meeting with chiefs in Ghana and drinking the schnapps and so on, and being in places like Vietnam, where not only were women a bit suspect in regard to mines, but actually just the authority of a woman in the early 90s in North Vietnam was they just wouldn't accept, the local geologists wouldn't accept to take instruction from a female geologist, an Irish female geologist at that time. So things have changed a lot. It's a soft skill. It's a really important skill. And, in terms of education, I've gone into schools to talk about geology, and the excitement is palpable with young people in there. And quite rightly, as Rose is saying, we have to keep on that road when they move into teenagers, younger teenagers and older teachers, to keep them engaged and to look at the curriculums in our school, educate our society, so that they understand the role we're playing. So I'm starting to ramble now, but look, I think fundamentally it's a human engagement situation where we have to build trust, we have to listen, and we have to, as Manuel was saying, we have to understand the needs of the local people. In Ireland, you go to speak to a farmer, you get permission to go and drill on his land. It's highly regulated. He wants to make sure you're not going to do any damage to his farm, where his livelihood has been, and all his generations before have existed on the land, and so on. So you have to build that trust and be a straight talker.
I agree with you, John, and everyone else. I mean, I've been in exploration for a couple of years, and one of the things that I need to do for the companies I've worked for is a community engagement, where you sort of need to go in and talk to people and tell them your intentions, right? And like everyone else said, you need to know the environment you're working on. Understanding what language they're able to understand, I think, is really key. Because I'm from Namibia. I don't speak Afrikaans, but a lot of the areas that I worked on, a lot of farmers spoke Afrikaans, and that was already a challenge. So I think knowing who you're dealing with is really key. And this brings me to the question to sort of say, what do you think are the non-technical or social skills and knowledge that we need to make sure we strive in making sure that we communicate well to local communities and other stakeholders? And I would like to start with Josephine. What are your thoughts on this?
I think, like John said, listening skills is very important. Putting away our head of expertise and knowing what we want, and this is for the best of the community, but not telling that in a very respectful way. So I think the first one, listening skills, networking skills, which most of us, in my case, I had to learn, because as a geologist or the geochemist, I'm just used to, paper and books and labs. And so really networking skills with people, that's very important. So yeah, I think listening skills and networking skills, those are, apart from the technical skills that we have, something that we should really try to enhance ourselves with.
Who else wants to jump in on this? Linkley, Rose, Manuel, feel free to jump in to sort of give us your ideas.
Yes, if you don't mind. I think the language, it's very important because different communities really speak different language, industry, a general public, even like you go to a school, like John said, we in ICRAG, we do a lot of public engagement, outreach, and we do need to practice our activities before going to the school because the language we use, normally technical language, it doesn't work with the 30 years old kids. So I think find a common ground, speak a common language is very important.
Brilliant, brilliant. Any other speaker that would like to jump in on that before we move to another aspect of the discussion? Rose, do you have something to say? John, Manuel?
No, I think communication, listening, I think all of that is, I agree with everything that's been said, really. I think we have a tendency to, geologists especially like to have specific words for such specific things that even within our silos within geology, you know, sometimes I don't understand a structural geologist. So taking a step back is so important.
I think as scientists, we deal with quite deep subjects, technical subjects, and we have to develop the ability to communicate in a simple, engaging, emotional way. And I think if you look at people like David Attenborough, I mean, he deals with huge subjects, but he brings it down to a very simple level. Is it Cox? His name is Cox, the astrophysics. I mean, he's talking about quantum physics, you know, and he's able to actually make us understand how far these stars are away. I mean, we have such fantastic things. Look at the time. They say you have to study geology to understand time. Maybe you understand study space or astrophysics to understand space, but it's an incredibly exciting thing we do. And we need to just be able to communicate. I've always found that generally people are really fascinated. They're fascinated with what we do. And we just have to harness that excitement and communicate simply and listen.
Brilliant, brilliant. Just one question before we sort of round up. I just have a question to sort of say, for us to really know that, or to say we are working in a sustainable environment, we need to touch on issues around equity, diversity, and inclusion. Do we think this is being practiced? Are we being equal? Are we being inclusive? And I'd really just like to hear one or two opinions, and then we can move on to sort of career advices and things like that. Who would want to take this question on equity, diversity, and inclusion? Is that being practiced at the moment? And if not, what do we have to do? I mean, we probably know what we need to do, but I would still like to hear opinions on what you personally think can be done. All right, Manuel, sorry to pick you, but what are your opinions?
I think nowadays the diversity, especially and inclusion in geoscience is not in the level that we would like, but it's better than before, as I can pick up. I have no much experience as a researcher or as exploration geologist, but as a student from the university I'm coming from, before I had that, you couldn't find more than 10 students, human students in geoscience class. But now the number is even. You can find 50-50, and it brings me to the conclusion that the things are getting better. Of course, not in the state that we would like to see, but I hope in the future the thing will be better. And this is one example. We have here this diverse team, including human, men, and that's really, really wonderful. Thank you.
Thank you, Manuel. John, I'm going to pick your brain a bit for 30 seconds. What career advice do you have to the youngsters in the room listening to this panel discussion? 30 seconds. Short and sweet, please.
Okay, I thought you were going to ask me about the diversity and inclusion part of it. But look, I got into the geology through tectonics, like we were saying earlier on the speaker, and interest in structural geology, and then you follow your path. Well, you know, I suppose in those days you go into soft rock geology, oil and gas exploration, hard rock geology, mining. But you should get engaged with your local chapters. There's plenty of opportunities out there for mentoring and guidance in the IGI here in Ireland. We're also seeing that a change in our student membership too, increasing amount of females. So yeah, there's plenty of opportunity out there to engage. SEG is a wonderful organization, obviously through mentoring and student organizations, and learn your basics, learn your chemistry, learn your physics and so on, and get your tools right, and then the world's your oyster. I think it's an incredibly exciting time, more so even than when I started my career. I mean, it's just a huge transformation. The world needs the metals. You got to get out there and you got to find them. So it's a fantastic time now to be where you are.
All right, thank you, Dad. Okay, just to round up the room, thanks for the great discussion. But before I let you guys go, I would like to get sort of around the room to sort of say, what are your individual views on, so what are your visions for the future? And so more like, what would you like to see within the larger economic geology community? So that just to sort of round out the room, what are your visions of the future and what would you like to see within the larger economic geology community? I'd like to start with Rose.
I think my ideal future would be, I think based on what we spoke about, when you bring a diverse group of people to the table, you naturally can address issues better because you have more diverse thought and you have more diverse opinions, and you start to realize, what's important to different people. And I think going forward, it'd be really great to see diversity increase within geology, to see numbers of students rising again. And that, I think, will naturally make geology a more sustainable place as we start engaging more people.
Brilliant, brilliant. Linkley, over to you.
Yes, I think it's a very good wrap up from when we started the sustainable development and to combining with economic geology. So economic geology really touched many aspects, geology, economics, and of course you can't avoid talking about the social and environmental impact. So how to achieve a sustainable development in economic geology? I think it really needs cooperations of all the sectors that are involved in the development. So that's what I would like to see in the future.
And I'm sure everyone agrees with you, collaboration. Josephine, over to you.
I totally agree with Linkley. Collaboration for me is one of the things that I would like to see, open to possibility with working with other scientists, trying to find scientific solution for a better future for our future generations. So I think in a nutshell, collaboration, communication, and engagement with everybody.
Brilliant. Manuel, over to you. And John, you'll be the last one to give us your vision for the future.
Yes, I wouldn't be so apart from what Josephine and Lyndon said. Collaboration of young scientists and scholars across disciplines and boundaries is of the utmost importance to achieve, for instance, sustainable development. But other things that I would like also to see within our community is a growing interest to learn how to effectively communicate issues related to our discipline to non-experts. And that's what we discussed here. So I think those are the things that I would like to see. Thank you.
John, over to you.
Yes, I guess career sustainability actually for economic geologists. We see an older cohort and a younger cohort, and then we've got a big gap in the middle. Now that is often a response to the mining and exploration response to metal prices and cycles in the economic cycles. And geologists lose their jobs in downturns, whereas that's not necessarily the case with other careers as much. So we need to have it more sustainable as a career, and I think that the governments have a larger role to play in that. It's going to require longer term planning and not just knee-jerk responses to the copper price going up and then the copper price going down, and then you close projects and you fire young geologists. So that's a major problem that we have, and we lose all that experience as we go through. Then people go off and they go into other industries and so on. So yes, I would like to see more sustainable careers being developed for geologists, and how that's going to be done. As I said, more longer term planning and maybe more government involvement.
Brilliant, brilliant. Thank you guys for your time and for an exciting discussion. But as a young geoscientist, I would also just like to, I'm not part of the panel discussion, I'm not a panelist, but I also like to sort of share my vision for the future. And I just want to touch on communication is really key, data access is really key, government, like John said, I think everything really boils down to what the government have in places. And we are in the great positions as young geoscientists to make sure that we contribute to making sure that our governments understand the value of what we have in our countries. And only then they can make rules and policies that favor both the investors and us as local people. And then the other thing, again, networking is really key. And it's also only through networking that we are able to sort of do this collaboration. Okay. And then overall, enjoy geology, and if you put all these aspects, I'm sure we can achieve sustainable development. Once again, thank you for your time, and thanks for the interesting discussion that we just had.
Thank you for the opportunity.
Thank you very much.
Thank you. Thank you.
Thank you for the great event.
All right. I would like to call upon David for the concluding remarks and the thanking words. David, are you available? I hope you did not disappear. Over to you, David.
No, I'm here. Just one moment. So, yeah, I would like to say a few things to wrap this session up before we play a longer video montage of all the perspective videos we got to lead out of this session. I hope you can see my screen now.
Yes, David, we can see your screen.
Excellent. So first of all, I would like to express our gratitude to all of our speakers and panelists. Thank you very much for your great contributions. And I would also like to thank everyone for attending, and I hope you enjoyed the session as much as we did. I'm very happy that we came together as geoscientists to celebrate Earth Day, and it's amazing that we can do it virtually across the world. And I'm curious from where you're joining us today, so I'm just going to start a poll, and please fill it out, and I'll leave it open for a moment, and we'll come back to it after a few slides. So we would like to send special thanks to everyone who sent us short video clips with their background and thoughts, and received almost 2 hours of material, and we played a montage to introduce everyone at the end of my remarks, as I just said. And while you wait for the second session this afternoon to start, we would like to urge you to check out these contributions in full on YouTube. These videos are a wealth of interesting stories, valuable advice, and important perspectives, and we can share another link to our YouTube channel in the Zoom chat. Another thing I would like to highlight for those interested in the SEG or already member of the SEG, I would like to draw your attention to the work of the SEG Early Careers Professionals Committee. Please check out their website at zegweb.org/ECP and reach out to them with questions and suggestions. And please also check out their videos on our YouTube channel. They offer really useful advice and present very valuable thoughts. And the SEG ECP committee also coordinates the SEG mentoring program. And if you are interested, I encourage you to check out the mentoring website, that is zegweb.org/mentoring. Just highlighting a few upcoming SEG events as well. The University of Las Vegas SEG Student Chapters is hosting an epithermal ore deposit short course on Saturday, and you can find the registration details on the SEG website. Then our own chapter has a lecture coming up on the Kupferschiefer by Professor Gregor Borg. And for registration details, please send us an email at nuiseg@gmail.com. The SEG will also host a Students and Early Career Professionals Mentorship webinar. And I think the details are now on the SEG website as well. Then there's an exploration careers Kickstarter hosted by Ore Deposits Hub, and you can find the details on their website. Another great initiative is the University of Toronto SEG Student Chapter hosts a Student Chapter virtual field trip competition where you can submit short videos of a field trip where you describe an outcrop related to economic geology. And the submission deadline is end of July, and again, details on the SEG website. And lastly, I would like to highlight that the abstract submission deadline for the SEG 100 conference is coming up, and that will be on May 3. And you can find the abstract submission details on the website seg100.org. Okay, so let's have a look at the poll results. We lost some people over this session, but probably not very surprisingly, most people come from Asia and Africa and Europe, which is great. Probably given the time, we don't have many attendants from North and South America. This is fair. But yeah, it's great that you're joining us from anywhere in Europe, from South Asia, Southeast Asia, and East Asia, as well as from Africa. Thank you very much for joining us. And yeah, we hope that the SEG Student Chapter Earth Day Symposium could become an annual event, each time hosted by a different chapter. So please have a thought about whether you and your chapter are interested in hosting next year's symposium. And get in touch if you have any questions. All right, with that, I would like to remind you of session 2, which starts this afternoon Irish time, or at 5 p.m. GMT. Please note that this might be different from your own time zone. And to finish, I will introduce everyone who contributed their perspective in another video montage. Thank you very much for joining us.
Hi, it's very nice to meet you in this video.
Hello, everyone.
Hello.
Hi.
Hello, everyone.
Hola.
Hello, everyone. Hi, guys.
Hi.
Good day, everyone.
Hello.
Hi.
Hi, everyone.
Hello, everybody.
Hello.
Hello, everyone.
Hey, everyone.
Hello.
Hey, everyone.
Hello, nice to meet you.
Hello, everybody.
Hello, everyone. Hi.
Hello, everyone.
Hello, everyone. It's a pleasure that you are watching our video. My name is Luis Alberto Pisano.
Hi, I'm Michelle Clark.
My name is Paul Castillo.
I'm watching you.
My name is Sarah.
Keshi Sitembi.
Giancarlo Daroch.
Hi, my name is Fernanda Alvarado.
My name is Zhang Xin.
My name is Doran.
Meu nome é Lúcio Massari.
My name is Hugh Richards.
My name's Ella Losbeck.
I'm Kaura Paeva.
I'm Gabriel.
My name is Alanis Olishbet.
My name is Mars Marv.
My name is Isaac Simon.
Thomas.
My name's Aaron.
My name is Chu Xianghan.
My name is Denis Achoki.
I'm Ada Rodriguez. Molly Ag.
Conde Wells.
My name is Renata Barros.
Fiona Best.
Benjamin Larenas.
Mary Barton.
Dan Smith.
Nalemi Zhengxi.
And I'm Liu Tong. And we are the first year graduate student of the Chinese Academy of Science.
I'm an undergraduate geology student from University of Barcelona.
From SEG Student Chapter, YGG class.
I'm an MGEO student at the University of Leicester.
With UNAM and also part of SEG here in Namibia.
Final year student at the University of Namibia. Eu estou prestes a me formar em Geologia pela Universidade de São Paulo.
I come from SEG Student Chapter and IGGCS.
I'm the Vice President of the Student Chapter of Barcelona.
I'm from Brazil. I'm master student at University of São Paulo. I'm also the president of the SEG Student Chapter here.
And I am a PhD student here at Monash University.
From the University of British Columbia in Vancouver, Canada.
And I'm a student from SEG Student Chapter at IGGCS.
I'm a fourth year applied environmental geologist here at the University of Leicester.
I'm doing my master's in applied geoscience at RWTH University.
Hi, we're both studying
at the RWTH Aachen University in Germany, and we're both studying applied geosciences in our masters.
And I am a final year student at the University of Namibia doing a honors degree in geology, and I'm also the SEG Student Chapter President of the year 2021.
And I'm an exploration geologist based in Santiago, Chile. I'm also part of the Early Career Professionals Committee.
I recently returned to academia as a PhD student at Colorado School of Mines in the United States.
And I am an exploration geologist based in the UK, working for Nordgold out at the Bisibuli open pit gold mine in Burkina Faso.
And I'm an economic geology PhD student at the University of Leicester, studying the emplacement of the Northern Bushveld complex.
My research direction is proper copper deposit in the Central Iron Organic Belt.
I'm currently doing a research project on the potential for a Norilsk-style nickel, copper, platinum group element sulfide mineralization in the Kalahari zone, Botswana.
And I'm majoring in or specializing in economic geology and petroleum.
And I'm studying on how to evaluate the ore-bearing properties of pegmatite in the Himalaya orogen belting. No.
I'm a PhD student at Monash University. I'm focusing on the transport and source of rare earth elements. Rare earth elements are really important for the future. They're used in wind turbines, they're used in electric cars, and Australia is full of them. So what I'm studying is how exactly these rare earth elements, where they came from, how they got to where they are.
The field I mainly study is uranium improperly. The problem I want to solve most is the beneficiation mechanism of it and where we can get it.
I am a PhD student and my project is about modeling igneous intrusions for 3D modeling software, and the idea is to improve how we are modeling the subsurface for resource management.
My project is to investigate the fluid rock reactions, especially the feldspar water reaction, especially key feldspar reaction and albitization reaction, because key feldspar and albite are always associated with IOCG deposit and porphyry deposit.
My research at the moment is based around deep eutectic solvents, which are a more environmentally friendly way of processing gold as an alternative to cyanide.
I'm currently working on my master's thesis, which is unraveling the Cretaceous and Cordilleran deformation related to the McMillan Pass shale-hosted massive sulfide deposits such as Tom and Jason, which you can see behind me.
My current research is rare metals. I would like to throw my own research on the status quo and the prospects of rare metal mineral resources in China to make an assessment.
I'm studying experimental petrology, which is basically making rocks, and I'm interested in putting critical metals into my experiments to see how they behave in deep earth conditions. Basically, how do critical metals move from the subducting slab into the mantle wedge, and hopefully that will give us an idea of how to figure out where and why they form eventually in the crust.
My certain research direction is the study on the genesis of sedimentary air deposit. To a certain extent, the study of such deposit can provide more evidence support for the evolution of the Earth's atmosphere and the development of life.
My current research direction is light rare earth mineral. I mainly want to solve the problems about the genesis of the deposits, including the source of ore-forming materials and the source of fluids.
My main research direction is Pegmatitic alkaline-related rare earth element deposits. Many countries consider them as strategically important resource. So in the future, I want to characterize magma source and ore-forming fluids.
My first motivation to be involved with economic geology, I would say, is that Brazil is a huge country with a lot of unknown potential. There's still a lot to study, a lot to discover around here.
I'm very passionate about geoscience and in particular economic geology, more so because it's a field that allows you to constantly engage with the build-up and structure of our planet Earth.
I want to become an economic geologist because I love geology, I love minerals, I love nature. It's all about love.
Meu interesse por mineração, geologia econômica, exploração mineral começou por causa das disciplinas ofertadas na graduação. Tive a oportunidade de estagiar no Serviço Geológico do Brasil, na gerência de recursos minerais.
I had a real passion for research and really enjoyed it, but I wanted to make sure that the research I was taking part in had wider implications and would influence the decisions of companies and the industry I was working within. And I feel like being part of the economic geology industry is the perfect way to achieve this.
My big interest is to contribute to make geological data more accessible and therefore properly used.
I chose to be an economic geologist, and it's interesting. It makes me feel that the development of my career is closely linked to the country.
My journey into economic geology began in my first year at the university, where we would be taught of several mineral deposits our country was rich in. Specifically, minerals like gold, lead, copper, zinc, and tin. So we would learn about these subjects, and I'd be very interested because I would think, what can I do to help my country?
And I am an economic geologist. I love being an economic geologist because I get an opportunity to merge science with my creative side. To me, being an economic geologist means understanding the processes that form mineral occurrences and then evaluating those occurrences for possible extraction. So yes, there's a lot of science in economic geology, but there's also quite a lot of creative thinking because you tend to think in 3D.
I currently work as lead geochemist for a large global exploration and mining company based in Perth. And for me, I've always loved being part of a skilled and highly motivating and generally really fun team. Through my job, I've worked on a diverse range of different ore deposits.
And I'm an Associate Professor of Applied and Environmental Geology at the University of Leicester in the United Kingdom. I've always loved geology and I've always loved chemistry, and economic geology or mineral deposit geology has always sat at the overlap between those two for me. A passion for the science and an academic interest.
I wanted to stay on this more sustainable approach, trying to make the world a better place.
I am really interested in economic geology because I think it's key for the development of countries.
And yeah, I'm really excited about economic geology. I really want to make a difference and be able to provide some kind of framework that we can find new deposits and learn how these systems work.
I want to become an economic geologist because I believe we are absolutely essential in order for the world as a whole to move towards a more sustainable way of living. We are all working towards the goal of decarbonisation, and the only way in order for us to do this is to mine those critical resources.
I am just so motivated to do something that has an impact on society and to actually help promote economic geology to other students so that they understand its importance in our future.
I was very interested in geology since I was young, so I chose resource exploration engineering as my undergraduate major. When I started studying geology, I found out that I fell in love with it. I'm curious about everything I observed in the field and like to feel the magic of nature.
We need all of these metals for the future, for renewables, for new buildings, for everything really. So the reason why I'm interested in economic geology is I love putting my skills to use to find these metals.
As we all know, mineral resource is an essential factor affecting the national development. So the interest and the importance of it caused me want to be an economic geologist.
I study geology and wanted to be a geologist because the mountain is near. Even you don't climb it, it's always near. When we looked up at the vast starry sky, we're standing on star too. I think it's really romantic to spend my short life exploring the everlasting gifts of the earth, rather than ups and downs of happiness and sorrow in a single day.
There is a proverb that says, if there is a career that you are willing to work for the rest of your life and never regret, then it's your calling. For me, economical mineralogy is.
As for me, it's a pleasure to be a member of Economic Geologists. It's a really nice chance to leave something meaningful to this world.
For the future of the economic geologist, I think it will be continued to focus on the new energy for energy conservation and emission reductions.
So many answers lie in the subsurface, but we still have a lot to learn about it. So it's really an exciting time to be a geologist.
Now, more than ever, the world knowledge is now accessible online, and I think there is a global transformation in the way that we have access to this knowledge. And I think that brought an opportunity for us.
As the next generation of rock stars, is that we'll be entrusted with more pressure to make new discoveries, expand existing ore reserves, and work in countries that or areas that have previously not been explored by the mineral sector for a variety of reasons.
We as ECPs have a big role to play. We need to make sure that we are helping people understand not only where, but how we extract the metals that they use every single day in their routine lives. And if we can do so across the world using our own networks, we then be able to communicate and broadcast this message across a wide spectrum of people and on a global platform.
I look forward to using my skills to make the world a more sustainable place, and especially assist in responsible use of my mother continent's rich resources. Thank you.
Thank you very much and stay safe.
Thank you, everyone.
Thank you.
Thank you, everyone.
Thank you very much.
Thank you very much.
Thank you.
Thank you.
I thank you so much for taking time to listen to this, and have a good day.